Alright guys, all the project files can be downloaded right here for absolutely free, updated in the Spectrum. But if it's easier, you can download them on Fab, add them, and everything will be there. If you're only here for the hologram shader, I've set it apart right here for you so you can download it separately. And if you need any additional shaders, then you can go to my Fab page and check out the free shaders I've made there. This version is already the second version, the one we just made, which we'll be looking at. And this version is the one I made a long time ago, the first version. And there are also shaders for stylized things like domes, barrier shaders, which we'll be developing further as we go through this course. Now, for whoever actually wants to download it, go ahead and download it. It's all free and very easy. Now let's break down how it all works. There are some settings here. Color correction settings are where colors are defined. Next, core settings. The core is the central point. It has a minimum and maximum size. Lower values make the core larger. If you specify different sizes, then the core will pulse at the speed you've set right here, just like this. Now what else can we do here? We can remove this value, set it to 0 to get rid of the core entirely. Good. Next we have the hologram. The hologram is the actual texture of the city or something like that. Right here we have the distortion strength. It gets distorted. Let's move over here. The distortion strength of this texture. Right here we have the distortion strength of this texture, just like that. Additional settings for power, range, brightness, and so on. You can just adjust all of this by eye right here. Nothing too serious, nothing critical. What's important is the speed here and the tiling size. The size determines how large the scale of the texture will be, just like this. And the top one controls the size of the distortion texture. So if we manually configure a substantially higher value, then the distortions will be these tiny small ripples. If we set the low value, then the waves will be large. Good. This is the speed, so we can set it in motion, just like that. That's it. Next, we have the lines. The lines are these moving lines right here. There are 3 levels of lines here. You can configure them separately, mix them, and give them different speeds. Don't press my buttons, go away. Take your hand away. Then we have the noise settings. If we remove it, the effect will become flat. If we add it, it will add depth, just like this, a sense of volume. There's a texture for it as well. You specify it here and adjust all the same settings as with the hologram. Then we have the last part, which is the masks. If you want to apply this effect to some objects that aren't a standard sphere, then you need to enable the triplanar projection option. What does that mean? By default, this effect works based on UV using UV coordinates. But as you know, different objects have different UVs and they won't look quite right. So we enable this expensive mode. It allows us to project this texture along 3 axes. So let's notice the difference. I turn it on like this, I turn it off like that, and that's everything regarding this effect. If you just wanted to download and configure it, then please go ahead and do so. And next, we'll be breaking down how to create it. In this case, I have a texture right here. What can we do with it? We can do the following. The very first thing we can do, the simplest thing, is to add this configuration. You should already know what desaturation is. It's saturation. It's key settings, what it can do. First of all, it can desaturate, remove the saturation of the texture. So here we have a texture, it's colored. We can increase this value to 1 and gradually bleach it out. And then we're interested in multiplication. We make the texture brighter or darker. We also raise it to a power, that is power. This allows us to make dark areas dark and bright areas bright. This is a basic setting. Next, we want to take Fresnel. What does Fresnel do? It allows us to create a mask that highlights the edges. And these edges, we clamp them in the range from 0 to 1. Remember, all masks must always be clamped in the range from 0 to 1. Why exactly would we do this? Because it will be much clearer for us to proceed with our work further. I can take this value here, carefully subtract this specific mask from it, and obtain this particular Fresnel effect, and get it so that my edges will now be completely black. What can I use it for? To start with, I will once again clamp it in the range from 0 to 1, and this mask, the hologram mask, I can use right here. Now my edges, they become quite soft. If I start increasing or decreasing the power level, you'll see that the edges will get softer and even softer still. So, depending on the angle at which we look at this object, its edges will be soft and there won't be these sharp lines. This is why this effect is created. I hope that's clear. We have a texture and we want to animate it somehow. The easiest way is a panner, add a panner and animate it. In this case, if we just add it and enter some value right here, it will be animated. However, we want to have control over it. We create a vector for, use the B and A channels to specify the speed, that is, to set the speed. You should already know this if you've watched, well, basically, the 3rd video in the playlist where I answered the most frequent questions. Then we also create a vector for and utilize the specific values of its B and A components to use it for scaling our elements. If we want to operate with UV, that is, work with UV mapping, we always need to call the texture coordinate node. Next, we want to increase the size. And in this way, in this specific way, we can easily set the value. So we set it to 5, and now our texture has become much smaller. If we set a smaller value, the texture will become larger, its overall size will become significantly larger, and so on. That is, we want to have full control over the size. Then that's not all we need. We've made it possible to specify the speed, and we've made it possible to adjust the size. Now we want to add distortion. By itself, if we take the texture coordinate and start adding something here, we'll see that our texture shifts significantly in the viewport. So if we take 0, everything will be fine. It's in the center. But if we start moving it, we'll see that our texture shifts in this direction. It shifts up and it shifts left, that is in 2 axes. But we don't want the texture to move uniformly everywhere. We know that we're working either with each pixel separately. This texture is 4000 pixels wide and 4000 high. So this should already be known to you. In this case, we're working with pixels. Each pixel in this texture also has its own brightness from 0 to 1. So we're saying that we want to use this texture to shift every pixel of this texture by the brightness distance of this texture. The texture serves as a shift coefficient for every pixel of this texture. Okay, now if we just take it and connect it in this way, we'll see that our texture distorts very heavily. We want to multiply it by a small value, 0.03, because this will allow us to create a slight soft distortion like this. We're adding all the same things we added for the hologram. Everything's the same, meaning movement and scaling, it's all identical. Just here, we're removing the upper channels, selecting RG, and that's it. The same thing applies. Absolutely everything we've done here is also applicable to noise. Here's our noise, same thing, just a different texture. A different texture, and that's it. And we created other parameters that control the noise. But otherwise, everything is the same. How does the core work? For this, you need to understand what Sine is. I suggest you watch this video by this author. He describes it well, explains it from a mathematical trigonometric perspective, meaning he uses examples to show what Sine is and how it works. But I'm not great at this math, so I'll try to explain it in a makeshift way, using simple words to say what it is. Sine is a wave. A wave that infinitely loops the values that go into it. It loops them in a range from -1 to 1. What does that mean? So everything we put in here, for example, we have time. The sine function is always, in 99% of cases, always used with a time variable. If we look closely at what constantly changing value is returned to us by time, we'll see that here we have a value of 7,100. What is that? 7,100 seconds have passed since I launched Unreal Engine. We can use time, which updates dynamically. It doesn't stand still. Time moves 1, 2 seconds, 3 seconds, 4 seconds. Time passes, so we can plug it into Sine and get the following. Let's look at the graph to see what's happening here. Right here, we have this number. Let's slow it down. Here's -1, at the bottom is -1, here's 0, and here's 1. Now our number rises from -1 to 1 and drops back to -1. And in this way, when we connect time, it works in a loop. And this setup, time, and Sine, they almost always work together. You just need to remember that they always work together and create this -1 to 1. However, in order for us to use it properly, what exactly is it that we want? We want to clamp it in the range from 0 to 1, because I've always told you, you always need to convert any values, any masks, into the 0 to 1 range. What specific steps do we need to take in order to convert the range from -1 to 1 into the new range from 0 to 1? It's already shown here. We need to add, first of all, 1. What happens? -1 becomes 0 and 1 becomes 2. If we add 1, then we divide it by 2. 0 divided by 2 is still 0, which is an error, but Unreal understands it. Then 2 becomes 1, a range from 0 to 1. This configuration setup allows us to successfully accomplish the following steps. Now we have an animated value that smoothly and gradually transitions from 0 to 1. Okay? So now that we have a mask, we save it into our system for future use. We can add an element here. We can incorporate a time-based variable into this specific section and divide it by a chosen number to effectively reduce the velocity and slow down the overall movement speed. This way, we will successfully obtain a high quality and finished mask. And we can use it everywhere. Black is invisible, white is visible, black is invisible, white is visible. That's how we get the mask. We take this mask, that is the range from 0 to 1, and we transform it, meaning we map it to a range from 5 to 6. So from 0 to 1, we map it from 5 to 6. Why are we doing this? We have a Fresnel, and this Fresnel creates a mask that has a very dark spot here for the core. We want to get this spot, but we want the central part specifically to be visible. In this case, we see that its center is black. If the center is black, and it should be white, and what do we need to do? We need to invert this value. We call this a specialized 1- node, and this allows us to effectively invert black to white and white to black. Now our center is white and the surrounding outer edges are black. We add a power node to achieve a much higher level of contrast. We add power and now it looks significantly more like a core. Now what else can we do? We increase the brightness levels slightly more and observe the specific result that follows right here. Now the value we have here, which is 7, we can create a dynamic animation for it over time. So we definitely need to animate this specific number. If it's 5, it'll be much larger. If it's 7, it'll be quite a bit smaller. So the higher the overall value here, the smaller the core becomes. Okay, we get that, and we want to animate its particular value using the animation we saved. Now we've mapped the value from 5 to 6 and effectively got this. So now the core gets bigger, bigger, and smaller. This demonstrates it well. This is how we get our mask. We have a linear gradient. That linear gradient creates a mask like this, completely black at the bottom, pure white at the very top. However, we must understand that a linear gradient works with UVs. It says UV gradient here, meaning a gradient based on UVs. In this case, if we use a UV gradient, then because our objects have different UVs, it won't work correctly. At first glance, it might seem like the same thing, but you should know they work differently. What does bounding box do? It takes the object's boundaries. In this case, if I select this object, go to the Show menu, Advanced, and check the bounds box. This object has its own orientation. It has directions for right, left, forward, back, and up, down. These are the 3 directions. In this case, we need a mask along the z-axis, which is the top. That's our b-value. So from the very bottom to the very top of these bounds, we want to get a mask. Why do we need this? We need it because the objects are of different sizes. This one is larger, this one is medium, this one is smaller, and so on. So all sorts of different sizes. Therefore, we get the following mask, and it will be correct for any object we apply it to. Then we can multiply this mask. Here we clamped it in the range from 0 to 1. So we have a mask here, 0 here, and 1 here. But we multiplied it by 15 here. Now the range from 0 to 1 has become 0 to 15. Why did we do that? We plug it into Sine, and it turns out we have 15 lines here. Why? Because we said that Sine animates, meaning it creates this infinite loop. In this case, we have a mask like this. We add time because we want to set it in motion. Here we specify the speed, and in this way we set it in motion. Then we duplicate this part several times. We duplicated it 4 times, combined it all together, and got the following result. In this way, 4 masks are blended on top of each other and create this kind of chaos. And ultimately, we raise the value to a specific power, then carefully saturate the result, and we get a final mask that looks exactly like this, also in the range from 0 to 1. And we know that an object has points, vertices, these vertices, and it has a boundary that I previously mentioned in the discussion. These boundaries, the object's boundaries, have a center. Here is the center of the boundary. Depending on the size of the object, their center will differ. And what does our object position do? It returns the center of these boundaries to us. Now, if we take a point, that is, the center is located right here. Let's say this distance is 1,000 units. So if we take world position, what did world position do? It returns the location of each vertex, that is each point. You should know what vertices are. And if we look at the topmost vertex, the topmost point, what will its location be? The size of this object, the ball, is 1 meter. 1 meter is 100 centimeters. So it turns out that if our center point is 1,000 units, then the top value will be 1,050. The bottom value will be 950. I think you understand the reason. Now, what do we do next? We subtract the object's center from this world position, so we subtract 1,000 from 1,050, which gives 50. From here, from the center to right here, it will be 50. And from 950, we subtract 1,000. So what do we get? Minus 50. So it turns out, from the center to the bottom, it will be minus 50. Since our values here are 0, here it's 50. We want to convert this into a range from 0 to 1. So what exactly is the process we need to follow? We need to perform a division by exactly 100. So if we divide it by 100, we can see that the resulting range becomes from 0 to 0.5 and from 0 to minus 0.5. We can't divide it by 100 because 100 is the size of this ball. But if we apply it to some other objects, for example, to this cabinet, then this cabinet's size will be significantly larger. If we look closely here, we'll see that its size is 190 in height. That is, each object has its own height, its own different one. Therefore, we want to divide not by 100, but by the object's size. We divide it by the object's size, and in this way, we get a mask along the z-axis. Along the z-axis, I remind you, that's B, the B mask. In this way, we get a mask that is 0 in the center, 0.5 here, and minus 0.5 here. And this will be valid, that is, correct for every object. And now we want to call absolute. What does absolute do? It changes. negative values into positive ones. What we had as minus 0.5 right here, minus 0.5, became just 0.5. Therefore, we have 0 in the center, 0.5 at the top, and 0.5 at the bottom. Just like that. However, we don't want the black part, that's the invisible part, black is 0, 0. This is the invisible part, what we want to hide. And we want to hide the top part and the bottom part, so we invert it. Called a 1 minus node. Now, the invisible part will be the top part, which is 1. Before, we had 0 here and 1, 1 here. Now it's 1 here and 0, 0 here. Now everything has been inverted. Again, we clamp the range from 0 to 1 and get the final mask. That's all regarding all these masks. What do we want to do next? Well, we can add black and white spots, meaning color variation, and we can add other tints for the color. How does it work? In this case, we incorporate the macro texture variation. So just open the file up here and copy this if you don't know how it actually works. We multiply any color by it and get the following. If we set the blending here to 0, we'll see that its spots are very thick. We want the effect to be subtle, so we set the range lower to 0.89. Remember, we are moving from the numerical range of 0 to 1. We always try to stay within this specific range. We carefully blend the colors together again with a subtle tint variation, that is, by using various tints. We mix it thoroughly and get the following result, so you can see there are many tints here. We introduce a parameter to precisely control the overall saturation levels of these tints, and another parameter to fine-tune the final mixing strength. Like this, how strongly it will be mixed. Next, we add noise to all of this. We remember the noise, this one. We multiply it by the animation mask that we animated together. We remember that we saved the animation, but right here in the 0 to 1 range, infinitely moving. In order to use it now observe closely as the pulsation occurs. You will notice that our noise will become significantly brighter and more intense. See how it clearly lights up and becomes much more vibrant every single time the core pulses in rhythm with the energy. For this, we added this kind of animation. Then we integrate all of this and perform a multiplication with this mask excluding the core. So why exactly are we doing this? And look, here we have a hologram. We multiply the hologram by these lines because we want the lines to work only with the hologram. Now, as a result of this process, we generate this kind of digital mask. On this mask, we add noise because we want the noise to be fully visible, while the hologram was together with the lines. So we don't want the lines to affect the noise, so we just incorporate the element separately. After we added it, we saw that at the top we have this stretching, this ugly artifact pattern. And to remove it, we supplement this with the height mask we created right here. This height mask allows us to remove the top part and the bottom part. We removed all of those unnecessary elements and we get a clean mask that we can multiply by the final result right here to ensure it blends correctly. And finally, we take the central core element we have positioned here in the center, and here as well, we make sure to incorporate it into the final composition at the end. Why is it essential that we add it at the very end of this process? This is because we want the central core to be visible, even if we are looking down from above. We remember that we created a mask, this mask, and if we don't add it, the Z mask will remove the core when we examine the structure from the top down, so we want to add it in at the very end. So that the core mask, meaning the core itself, is fully visible from all possible angles, okay? And that's everything regarding this effect. The last thing is this eye adaptation. This allows our effect to maintain the same brightness regardless of the post-process exposure. So no matter how you set up the post-process, this hologram shader will always have the same brightness in any scene. One last thing, the last thing I want to say. I won't go into these details because I want you to be able to figure this out on your own. Here we've added manipulations that allow us to edit, meaning change the UV size and so on for this texture. Now, the technique I used here is a triplanar texture projection method. There is a world-aligned texture function available. Inside this function is what I copied here. I just copied all of it, pasted it here, and adjusted it a bit because we need a texture that will be projected from all three sides, from the three axes X, Y, Z, or from the left, right, top, bottom, and front, back. It will be projected from three axes. We create three textures, and for each of these textures, we do exactly the same thing we did right here. For this texture separately, just select specific axis here. That is, use the world position rather than utilizing the standard texture coordinate, meaning texture coordinates. We are going to take the world position data and proceed to divide that value by the specific size, the tiling, and use it right here for each axis X, Y, and Z title. These are the three axes. It is the same for distortion. Create three textures, ensuring that every single parameter remains absolutely identical across the board. This is already a mask to select, to highlight left, right, and highlight top, bottom. See, the side where left, front, back, and top, bottom are selected. Here's the mask, where we can select a certain side. One side, left, right, top, bottom, front, back, and so on. If you remember, I said that if you want to learn how to create, you need practice. Therefore, the project files will be available to you. Repeat what you see, try to understand what's happening here. If you have any questions, feel free to ask them.